Okay, we've got mini exam to turn in today, if you're turning in. And then I'll give you your other ones at the end of class. So you're turning in, just put them right there. Thank you. Thank you. Anybody else? Minnie? Okay, thank you. Okay, I have a handout here for you. I think I have enough of these this time. Okay, you're welcome. In case he comes. There you go. Mm-hmm. Okay, I think we'll start with the handout. All right, we ready? Let's see, I'm recording and my microphone's on. All right, so last time we were talking about, hold on a second. This does not seem right. Hold on. Go back to the beginning here. There we go. So we were talking about surface integrals last time, and we determined that if we're given a scalar function of 3 variables and some surface S where we could come up with the parametric or vector equation that would draw this surface, where our 2 independent variables are u and v, so u and v belong to some domain, that the surface integral with respect to surface area of the scalar function over the surface S is this. This is the actual computation that we do. It's a double integral over the domain D of u and v of the scalar function evaluated along the surface, and then times the magnitude of the cross product of the partial derivatives. And so geometrically, we have some surface in 3-dimensional space, but it's not possible for us to visualize the domain. The domain is almost like 2 clocks running in the background. One clock is controlling u, the other clock is controlling v. But the surface itself is being drawn as we vary our u and v through their domain. So that's one thing we did. And then we said there's a special case where when you do the surface integral, if the surface itself can be drawn, or it can be looked at as a function of 2 variables only. In other words, the z-coordinate is some function of x and y, then we are in the special case, and what happens is this surface integral becomes the double integral. Instead of evaluating the function along the surface, we evaluated x, y, and then z, which is our function of x and y. And then the magnitude of the cross product of the partials becomes easier, and we just have a quick formula for it. All right, so this was the case, which this time we can visualize our domain. Our domain D is our restrictions on x and y, so it lives in the xy plane. Our surface is a function of x and y, and so this is our classic surface when we first started talking about functions of 2 variables. So this is one shortcut that we could use, and what I did not get into is why. I said I could show you, and I think we decided not to. But in this handout, I've actually gone through and explained why this thing, or where this thing comes from. Okay, so I do the actual work right here. I take the partials and I cross them, I take the magnitude, and you can see where it comes from. But what I did not do last time is show you how you could do a surface integral if your surface S is a function of x and z instead of x and y. So this time, your domain, your two variables in your domain are x and z, which means they live on the xz plane. So your domain is over here on this wall, and your surface is out here somewhere. Then you can also do a surface integral. Same way, you evaluate your scalar function at x, at y, which is your function of x and z, and then z, and then this part right here, again, changes. It becomes something different. So it's very similar to the previous formula, but there's a couple of differences here in the partials. Okay, so it's just another shortcut. And then I go through and I explain where that all comes from, okay, the computation to get this piece. And then there's one more possibility for a shortcut, which would be if your surface is a function of yz. So this time your domain lives on the yz plane, your surface is out here, then this becomes your formula. And again, I go through the explanation as to where that comes from. All right? So that's kind of where we are. We ended with an example, and now we're going to pick up where we left off, which was talking about, we're going to get to flux, but we got to start with this. So we're going to talk about something called oriented surfaces first. So an oriented surface is a two-sided surface, and I put here, there are examples, or there are one-sided surfaces. Does anyone know what the classic example of a one-sided surface is? Well, we could argue that the sphere has like an outside and an inside. You know, you could be on the outside of the sphere, or you could be on the inside of it. Does anyone know of, you're shaking your head, yes? Can you think of one a surface that only has one side? Well, you may have heard of it, you're just not sure. Here, Tora Bora, what? Tora Bora? Bora Bora? Have y'all seen this before?
Yeah. The Mobius Strip?
The Mobius Strip. So the Mobius Strip, you know, just this right here, we would consider that two sides, right? My index finger and my thumb are on the two different sides of the surface. But if I take this and I twist it and I paste it together, then if I do that, then my index finger and thumb are on the same side of this. So you follow it around and you'll wind up touching your thumb, then you keep coming around, you'll come back and you'll be on your index finger. So this is an example of a one-sided surface. We are not looking at this. We are looking at a two-sided surface, all right? So an oriented surface is a two-sided surface in which the normal vector at every point on the surface exists such that the normal vector varies continuously over the surface. With surfaces like these, we can choose two possible orientations. So the main idea here is that you have some surface. To say it's an oriented surface means that if I take the normal vector, remember the normal vector is going to be orthogonal or perpendicular to the surface. So, you know, if this thing's kind of, you know, waving around like that, then at every point there is some normal vector, right? It changes, but there's a normal vector. As long as that normal vector, we have a normal vector at every point, so it exists, and the normal vector varies continuously. So as I move around, the normal vector is changing, but it doesn't like drastically go from here and then flip over. Like there's no weird like jagged edges that cause any sort of strange things to happen with the normal vector. Does that kind of make sense? As long as we have that, then this is called an oriented surface. And if we have an oriented surface, then there are two possible orientations we can have. We can have a positive and a negative orientation. In other words, you can look at the normals coming out this way, or the normals that would have been out the bottom, all right? Right? I mean, there's two different normals. One out, one down, one up, one down. But this surface can be tilted any direction. So the main idea is that there's two orientations. We will call one of them positive, the other one negative. So whichever one we call positive, the other direction we will call negative, all right? The most basic example is a sphere. Okay, a sphere is a two-sided surface, and we could look at all the normals pointing away from the sphere, And we could call that positive orientation. And then negative orientation would be all the normal vectors that point inside, right? But it doesn't have to be a closed surface. It doesn't have to enclose a solid or anything. It can be any surface. Now, whenever we have a surface, if we wanted to actually compute the normal vector, then what we would need to do, and we've done this before, is we first have to be able to draw the surface, so we need some parametric representation of it. And then once we have that, then we would take the partial of r with respect to u and then v, and then cross those. Those would give us our two vectors that are tangent. We cross them, and that would give us our normal. And then we could divide it by its own length, and that would give us a unit normal vector, right? The length of this vector would be 1. Agreed? Because we're dividing it. That right there would be a normal vector, but dividing it by that creates a unit normal vector. And then negative n would just be the vector that points in the opposite direction from that. Now, in the special case where our surface z is a function of x and y, so that means truly our domain is the ground, then when we do that computation, okay, it turns out to be this. This will come into play a little bit later, but this formula here becomes this formula. So I'm kind of already doing all of that crossing and everything for us, and this is at the end what spits out. Okay. Oh, all right. Now, closed-oriented surfaces. If the surface is closed, that means it encloses a solid like the sphere. Then positive orientation is the one in which the normals point away from the solid that it encloses. So if you have a surface that somehow encloses a solid, so this surface would be everything here, then if E is the solid that it encloses, positive orientation is where the normals would always be pointing away from that solid E. Does that make sense? That's positive orientation. And then negative would be pointing in. So remember though, if we just give you a surface, or if we have a surface S, right? We have normals, if it's two-sided, right, an oriented surface, then it's not necessary that up is positive. All right? We have to say what we want positive orientation to be. We will say positive orientation for us here would be up, and then all the vectors down would be negative orientation. Here, positive is always out away from E, and negative is always into it. Okay, now we get to the crux of today, or at least the first part of today, and that is the surface integral of a vector field over a surface, which is often called in physics flux. So if you've already heard of this, hopefully I'm not going to bore you with this analogy, but the analogy that I've seen the most is thinking about water flowing through a river. Okay, so if you imagine taking this like a fishing net. So I've got this net. I don't plan on catching fish with this. I have a net, okay? And I'm going to place this net into the water. Let's say the water's flowing this way through, right? And this water, there's turbulence and stuff, and so all the little molecules of water are bouncing off each other. And even though the river is flowing, generally in this direction, at each point, each molecule might be headed maybe a little bit that way or a little bit up, or so. Does that make sense? Like at every point. So if I just kind of put this net through into the water, we're going to act like the net is not going to impede the flow of the water. It's kind of like this magic net that doesn't slow anything down. All right. Then what we're going to try and do is see if there's a way. If we call this net S, our surface, we're going to try and measure the net flow of water through this net, through this surface. So what we need to do is break up the net into small little infinitesimal squares and try and measure the flow through each square. All right? That's the general idea. Now, if we put our net this way, we're going to get a certain flow through here, certain flux. If I tilt my net this way, right, then everything's still going through like this, but we're no longer like perpendicular to that flow. We're a little different. So our flow is going to be a little different because of the way the molecules are coming through here. So we should have a different flux if we tilt it this way. If we go completely perpendicular to the flow, then we might get a flux of 0, right? It depends on the flow itself. So the vector field is going to be our flow, all right? S is going to be our net, and we need to somehow add up this net flow through here, all right? So the way we're going to do it is we're actually going to go back to chapter 10, section 3 on the dot product, and we're going to talk about this thing called the component of U onto V. And we had a picture of this way back in the beginning, right? Remember this? It gave us two vectors, and we said, hey, if we take this blue vector, we can project it onto the red vector, and it creates this purple vector. And we can actually find that purple vector. It's called the projection of U onto V. And then we could also talk about the length of the vector. So the vector itself is the projection. The length of the vector is the component of U onto V. And we did have two formulas for these. The projection vector was this one. If you project U onto V, you get this. But the component of U onto V was a much cleaner formula. All it said was what you need to do is take the two vectors, dot them, and then divide by the length of the vector you're projecting onto. All right? So I'm about to use this. Just wanted to kind of refresh your memory there. So let's say that we have a vector field. All right? So there is a vector field here. We're not going to look at it because we know it'll look messy, right, if we try and put it up here. But there's vectors all over the place, and the sphere is our net, okay, in the water, so to speak. And so what we're going to do is we're going to go and we're going to look at this little infinitesimal patch, and we're going to see how is it that we could figure out the flow just through that patch. And then what we'll do is we'll add up all those answers over the entire surface. So let me move myself. This is way too big. That might be too small. Can you all see that all right? Okay. Let me move myself over here. Get myself over here. There we go. I'll make that a little bigger. Okay, so right now I've moved to this single point right here, and I have a couple of vectors here. I have the green vector, the red vector, and the black vector, all right? The green vector is the field, okay? That's the vector field vector. So that is just coming out at whatever direction with whatever magnitude the field is telling us it should be coming through at that point, right? So this is our field vector. And then the red vector is the unit normal vector. Okay, so on any surface, right, any oriented surface, I have a unit normal vector, don't I? So this is going to be the red one here is our N, unit normal vector. And so what is the black one?
Will that be our projection?
Yeah, that's your projection, okay? This black one is the projection of the F onto the N. With me? So what we're doing is we're saying the field in this direction, we're basically taking the field in this direction, we're saying how does this vector projected onto my normal, what does it result in? So we're, instead of looking at the vector with a little bit of kind of angle to my net, I'm saying what is the contribution of that vector straight out of my net? And so I project it onto the unit normal one, and then that gives me the black vector. Now what we're interested in is not the projection of that. We don't want the vector, we want the length of it. And that will tell us basically the rate at which we are flowing through that point. Does that make sense? So we want not this, we want the component of F onto N, which by definition is F dot N over the length of N, right? Isn't that we just 10.7 told us that if you want to take the component of U onto V, it's U dot V or V dot U, doesn't matter which order you go, and then over the length of the vector you are projecting onto. But what do we know about this? What is the length of N? It's 1, right? Because we're saying that N is the unit normal vector. So this is really just F dot N, right? That's all that is. Okay, so this would give us a number, right? This would be a number. A vector dotted with a vector should give us a number. That number should represent basically the flow out at that point. Now what I want to do is take that and multiply it by the area, the surface area of an infinitesimal little patch. Okay, because we can't do it at every single point. We can do it at little infinitesimal patches. Multiply those two, and that should give us the flow through there. Does that all make sense? So with that picture, let's see if this formula makes sense. First is the notation we use for flux, which is we have a double integral over the surface of F, the field, dotted D, and then now we have capital S with a vector on it. So this is the notation we're going to use to represent this idea. And what it is we're going to add up over the surface S all of those F dot N's, and then we're going to multiply them times the infinitesimal little areas, these little infinitesimal, I got it out of here, but that little infinitesimal that I had there, that right there is like our ds, D capital S. So we're taking this number, multiplying it by that number, and that gives us what the flow at that little patch is, and then we add them all up, right? Okay, now this becomes this, and I want to show you how that happens. Are y'all following geometrically? This all makes sense? Okay. So now I want to show you why this formula becomes this formula, and I actually have that on the handout I just gave you. Where are you? Come here. Okay. So this is your flux. All right, so this is the flux, right here. So this is the the field dotted with the normal, right? That's the definition of it. And then times the little area of the infinitesimal patch. So what is F? When we say F, what we really mean is the field itself evaluated along the surface. The field evaluated on the surface, dotted with the normal vector. What is the normal vector of the surface? Well, it's the partial of r with respect to u cross partial of r with respect to v over the magnitude of it, right? Okay, so this. And then what's ds? You have to go back to last class. D capital S is this piece right here, right? That's from last class. So like if you go back and you look at last class, when we had this right there, this would give you the surface area of S. Okay, this right here was this part. So we integrate over the domain, which is our domain is our restrictions on U and V. And you see what happens at this point right here? These cancel, right? This cancels with this. And because those cancel, you're left with this really equals double integral over the domain D of F dotted with that, which is just the cross of the partials, and then with respect to area. Okay? So it looks like all we're really going to have to do to calculate flux is take some partials and cross them, right? Evaluate the field on the surface, evaluate over our restrictions on U and V, and we're in business. So there's not even any like square roots of stuff in here like we had with the surface integrals. It's kind of nice. I should maybe point out that everyone agrees, hopefully, that this right here would give you a scalar function, right? Because it's a dot product of two vectors, that's going to be a scalar function. So at the end of the day, calculating the flux is a surface integral over a scalar function ds, which is exactly the very first thing from last class. It's the integral over surface S of a scalar function ds. So our flux integral really turns out to be a surface integral. All right, let's do an example. So we want to calculate the flux of the vector field yzx across the unit sphere. So we want to do this. We want to calculate well, I'll write it like that, yeah. All right, that's what we want to do. Now we have a formula for this, that this says that this will be the double integral over d of f, right, evaluated at where? So this, I put on your formula sheets, I put A, B, C, you see that? So we could refer to these. So I'm using formula, where am I at here? Formula E, right? You'll see formula E. Okay, so I'm using the one that's boxed, but I'm going to do a little bit more. I'm going to put R of t in here. Or sorry, not R of t. That's not a curve, it's a surface. R of uv. Dotted with partial of r with respect to u cross partial of r with respect to v dA. So where do you think we should start? What are we going to start with?
Turning our field into terms of u and v.
Okay, we need to get our field in terms of u and v, which means we need to know how u and v come into play here, right? U and v are what we use to draw S. So we need to draw a sphere. That's what we need to do, right? We need to draw the unit sphere. So we need to come up with R right now. R will, the vector equation for R will draw our surface. So our surface S is the unit sphere. And in terms of a vector function of two variables like that, how do we draw the unit sphere? We've done this now several times, right? Did it several times last class. So it's what? So, wait, say again? Cosine. So we do have a radius of 1 here. So you get to choose how you want to use the u and v. So u can be like the theta or like the phi. It's up to you. So I don't care. I don't remember. Let's be consistent. How did we do it last class? Did we do... The u was like the phi, right? No.
U was the in the last class we used u as it was cosine of u as well. So I think
was it cosine u? Yeah. So u is the theta and v was the phi. Okay. Yeah. So what is it? Sine v cosine u, right? And then sine v sine u. And then cosine v. Is that what we use? Please, someone look in the look from the notes from last class. Is that what we are using for the unit sphere? If anyone took notes. We used u as phi?
we used u as phi, yeah.
See, okay, that's what I thought.
My bad.
That's all right. I just want to make sure we're being consistent here. So should I switch it?
No.
No? Don't switch it? Don't. You wrote it in pen. Well, you shouldn't write it in pen. What do you want to do? Leave it? Switch it? Switch it? Switch it? Switch it back to what we did last class. Sorry about that. Okay, so this is going to be sine u cosine v, sine u sine v cosine u. Okay, what are our restrictions on u and v then?
They both start at 0.
Okay, they both start at 0. We want to draw the whole thing, right? The whole unit sphere? So u is going to go between where? U's the phi, right? Phi is going to go here all the way down to pi. And then v will go 0 to pi. We good? Okay. Let's see if that's the way I did it. Yeah. Okay, now what? We've got that. Great. Wonderful. Now what?
Take the partial.
Let's do the partials, which again we did last class, but we'll go ahead and do it again. Partial of r with respect to u would be cosine u cosine v. And then partial of that one with respect to u would be cosine u, right? What am I? Yeah. Cosine u sine v. And last one, negative sine u. We even did crossing last time, didn't we? Didn't we cross these last time? Yeah, we did. Negative sine u sine v. And then sine u cosine v. And then 0. So let's save ourselves some time. What are those crossed? I have it right here. I can just write it down. Okay, I think we get, someone can double check. Sine squared u cosine v, sine squared u sine v, and our last one simplified to be sine u cosine u. That's what you should get when you cross these two. All right? Okay, so we have this part of the formula, right? We know our restrictions on D, right? D is the domain of u and v, which we have over there. And then now all that's left is we need to evaluate our field, which is here, on the surface, which means we're going to replace y with this. We're going to replace z with this, right? And replace x with this. And then we have to dot the two. Okay? Here we go. I'm going to write it all down before I dot it. I'll leave that there. So this double integral becomes the integral, let's see, I'll keep it over d for now. I'll put the limits of integration in at the end. I do my field dotted with the cross product of the partials, dA. So I'll fill in my cross product of my partials first. Okay, and then the beginning, the first one, is our field evaluated on our surface. So what's our first component? It's y, right? So and we're looking off of the surface, right? So the y is sine u, sine v, comma, now z, which is cosine u, and then x, which is sine u cosine v. We good? Yes?
So if the field was something more complicated, like y squared over 3 or something like that, you would have to start doing that. Like if it was over the unit sphere, you got to start messing with.
Yeah, if it was a more complicated vector field, then yeah, we would probably have a more complicated vector function over there. But in all honesty, you would actually probably try and do this problem with Chapter 13, Section 9, if it was more complicated, which we haven't done yet. Yeah. So there is another way to go after this problem. Okay? Y'all ready to dot that? Doesn't look fun, but all right, let's go double integral again. Let's just keep it over d for now. All right, so dot products are the easy ones, right? You just multiply components, add them all up. So when I multiply here times that, I'm just going to write down what I have, okay, because I don't feel like looking at it up there. Sine cubed u sine v cosine v plus sine squared u cosine u sine v, and then plus sine squared u cosine v cosine u.
Yeah.
Somebody can check, thank you. Okay. And I think because of time, I don't want to rewrite this. Let me go ahead and erase D and change my dA. And let's go ahead and put our limits of integration here. And because our u and v are bounded between constants, it doesn't matter the order we do these. So I'll go 0 to 2 pi on the outside. I'll go 0 to pi on the inside. Now that does dictate what happens here. Here it's going to be d what, d what? du dv? Du dv. So you've got to integrate all that with respect to u first, right? So we're not going to do it, but let's just talk about what we would do. If we were integrating this with respect to u, sine cubed, how would you integrate sine cubed? Yeah, this is a Cal 2 problem, so this is where you would like rewrite this as sine squared times sine. You'd rewrite sine squared as 1 minus cosine squared, then you do basic u substitution. That should be fine. And then sine squared, you'd power reduce, and then that one, oh wait, those aren't the same. Power reduce, power reduce? Okay, so then we get through that integration. Go ahead.
How about cosine u, so you could just do the u sub there.
Oh yeah, oh good, I'm glad you, yeah, I'm sorry about that. I didn't see that this cosine u. This is basic u sub. Yeah, power reducing wouldn't work. It would be more, it'd make it more complicated. Yeah, just use this and du's right there. We have it here also?
Yep.
Oh, okay, yeah, that would work out great. So you could do that step, right? And then on the next step, you'd have to integrate sine v cosine v. That's a basic u sub. And then just integrate sine v, that's easy, and then cosine. So this should all work out. I think I have, but it's a little bit of work, right? We all agree with that? I didn't put the answer here. So let's leave that as an open question right now. I'll type it in later, okay? So equals something, but we can do it, right? We can do it?
Yeah.
All right. Let's take a look at another one. Or let's see what's next, hold on. We have special cases. So in the special case, again, where our surface can be looked at as a function of two variables, in this case x and y, so our surface is floating above the xy plane, then our computation for flux becomes a lot easier to do. And here's the formula for it. Now, I've taken the time on here, where is it? Formula F. So take a look at formula F on that thing I handed to you. So it's surface. This is the formula F, right? Sorry, I'm moving fast there. So let's say that you're trying to do a surface integral of F over some surface. So you're trying to calculate the flux. And you're given some vector field, PQR, all right? So you have its three components. In the last problem, it was what, like, what was it? Y, ZX or something, whatever it was. We have our three component functions. And then we have an oriented surface S where it's given that Z is a function of X and Y. Then if we take R and replace U and V with X and Y, then this is what it would look like. You know, U would be U, V would be V. In other words, X and Y would be X and Y respectively. But our Z would be, oops, am I missing an angle bracket there? I am. There's supposed to be an angle. I'm missing it on here too. There's been an angle bracket right here. And Can I fix that real quick? Or, not very good. There we go. Okay, so we have this, and now if I take the partial of this with respect to u, which is really the x, then we get 1, 0, and then partial of that with respect to x. Partial of that with respect to y would give us 0, 1, and then that partial with respect to y. If I cross those, I get this, and now that goes into our formula. So when you plug that into our formula, you're supposed to take our field dot ds. This is our field. We're dotting it with the cross product, and when you cross those, you wind up just multiplying this times this, plus this times this, plus this times this, and you get this. So this is our shortcut formula when our surface is a function of x and y. All right?
This was a dot between q and gy, correct?
Between
So
q...
you're saying multiply together.
No, this is multiplication, because p is a scalar function,
Yeah, okay, yeah.
right? And g, this partial is a scalar. So this dot is not a dot product. That's actually just multiplication. Sorry.
But you get to it using a dot product.
Pardon?
You get to it using a dot product.
You get to this using a dot product. Yes. Yep. Now, there's something I should point out here. This is the formula we use when our surface is a function of x and y, right? But it's very important to understand that this is the formula we use when our normal vectors, I should have this written here. You know how we use the formula to calculate flux? We had to have a normal vector coming out of our surface? Yeah. And that normal vector could be oriented one of two ways, right? In this case, if our surface is like this, our normal could be pointed up or down, right?
Yeah.
This formula works when your normal vectors are pointed up relative to the xy plane. I thought I had that written down on here.
Something on the top right.
Is it top right?
Notice C component positive, so this is points up.
Yeah, so in that case, I thought I had it more like defined more like, hey, everyone, look at this. So I thought I drew it on here. But just remember, all of our little normal vectors that we're using for flux are pointed up. That's going to be critically important in a little while. You have to know which way you want your normals to use this formula. What if we wanted to use this formula, but we wanted our normals pointing down?
What do you put negative?
You just change this whole thing with a negative. Okay, so that would become positive, positive, and minus. All right? Now, just like before, we also have special cases, 2 more special cases. So let's look at this one. What if we're given a vector field, PQR, we have an oriented surface, but our surface now is that y is a function of x and z. So it looks like this. Our domain's on the xz plane. Our surface is out here. Then we could go through this whole thing again and construct what the cross products would be. But the most important thing is that when you do this, you get this right here. Okay? That's what you would get if you took the partials and crossed, the partials and crossed them. However, when you do this, look at this normal vector. I mean, this is the cross product, right? So that's a normal vector. It's not a unit normal, but it's a normal vector. Look at the y component. It's negative, right? So negative on negative y means, you remember, like x, right? Y, and then z. So negative y means we're pointed in that direction, aren't we? So if you look at this surface, if you use this formula right here, your normals are actually pointed that way, aren't they? And to me, that's not very natural. To me, the more natural normal vector would be the one that's pointed out to the right. Do you all agree with that? Yeah. So I am going to use a formula that I'm going to change this, and I'm going to multiply it by -1 to make it point out down the y-axis, down the positive y-axis. And so in our formula, we're going to use this. We dot it with the field, and we get this master formula right here. Okay, so this is the formula you will use if y is a function of x and z, and you want your normals pointed out to the right. Got it? One more to go. What if your surface is x is a function of y and z? That might be a typo. Is that a typo?
It says y.
It doesn't say y on there?
So I think it's supposed to be x.
Yeah, I left it red here so that I could remind you to change that. So I'm looking at formula H here. On H it should say x is equal to g of yz. So now your domain is on the yz plane, your surface is out here. If you go through all the mess with this and crank out the cross product, you'll get this vector, and you'll notice that the x component is positive, which would point out that way, right? Which seems pretty natural to be coming out at us, right? So we're not going to mess with that formula at all. We're going to leave it just the way it is. And then when you put it in with the dot of the field, you get this. Do y'all understand what I'm doing right here? Do y'all get this part?
Yeah.
This is me using like the original formula with r of uv, but replacing, whatever, the x with x, y with y, and the z with the function of x and y. Or in this case, replacing x with the function of y and z, y with y, z with z, and then doing all the partials and crossing.
Yep.
Okay, so that's it. We've got these three formulas now, in addition to the original one. Find the flux of the vector field f of x, y, z equals xy, comma, yz, comma, zx across the surface S, where S is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above the region where x is between 0 and 1 and y is between 0 and 1. Use upward orientation. So what I'm telling you is that I want you to do the flux through this. I want you to use normals that are pointing upward, all right? So how can you do this? Okay. Can we use any of the shortcuts? So if we look at this, formula E is the formula we use if our surface is just drawn like the sphere, right? The sphere is not a function of x and y, right? You can't look at a sphere as a function of x and y, or a function of y and z, or a function of x and z. But if you can look at the surface as a function of two variables only, like x and y, so z depends on x and y, then you can use either formula f, g, or h. Which of them will we use here? F, because z is a function of x and y. So this right here, this is our g function, right? Do we have a good domain restriction on x and y?
Yes.
Yes, it's given to us, right? So we got a good idea, a good grasp of the domain, D, right? So this is going to give us our domain here. My field here, I know what P, Q, and R are. P, Q, and R are here, right? And so using this shortcut formula, I just need to calculate the flux. I just need to do what? Negative P partial g with respect to x minus Q partial g with respect to y plus R dA. Now, am I supposed to use this formula, or am I supposed to change it, like multiply it by -1? Use it, right? Because this formula is good when the normals are pointing up, which is what we're being told. Do this with your normals pointing up. So that's our formula. I mean, do we know what P is? Q, R, yes? Can we take the partial g with respect to x? Partial g with respect to y? Do we know our limits of integration? We're in business, right? So let's do it. This will be integral, let's see, double integral. We got 0 to 1 on both, so this really doesn't matter. All right, negative P. What is negative P for us? So let's be real careful here. Negative P is negative xy, right? So negative x times y, and then times the partial of g with respect to x. I'm not going to write it down because I trust you can do that in your head, right? What is it? Negative 2x. We all good? Okay, and then minus q. So minus q. What's q? Y times z, right? Y times z. However, what's z? So why are we going to switch z over to this? We need everything in terms of x and y, right? So we're going to use this equation for z to replace that z right there with all that. Make sense? 4 minus x squared minus y squared. Okay? That's q, right? That's minus q. What do I still have? Partial g with respect to y, which is negative 2y. Okay? And then plus r. Plus r, but what's r? Z times x. Again, z has to be replaced. That's z, and then x. And then I'm done with that part. And then I can go dx dy or dy dx. Doesn't matter here because they're both 0 to 1. So I'll go yx. That's it. So all this would be is cleaning up at this point, right? Like just put these together, distribute, get all your signs correct, distribute, and that'd be integrating polynomials, and that I think would be well within reason. 713 over 180 is what you should get there. Questions?
So that's just the overall flux. It's affecting the vector field in this case.
It's what? Affecting the what?
So basically, I understand how you got the number. I'm just trying to understand what the number stands for, what the number means.
It's measuring the net flow through that surface of the field.
Okay, so it's just
it's a numerical value. It's a number, right?
Yes, it's not a flow that's going through this vector field that's given to us. Okay.
That's right. So if it's water, it's like, cubic feet per unit time. It's a rate of flow, so it's per unit time, so to speak. Any questions on that? Okay, let's look at this one. Find the flux of the vector field F, which is the vector field 0y, negative z, across the surface S, where S is the part of the paraboloid y equals x squared plus z squared, with y between 0 and 1. And then the disk x squared plus z squared less than or equal to 1 with y equals 1. And it asks for us to use positive orientation. Okay, so hopefully we recognize that this right here is a paraboloid that opens down the y-axis, and we're restricting y between 0 and 1. So here's the picture. The y-axis is going this way, so our paraboloid's opening out to the right, and it's being cut off at 1, y equal to 1. But then this right here is this disk, x squared plus z squared is less than or equal to 1, with y being stuck at 1. So that draws me that disk, but my y-coordinate is 1. Got it? So our surface S is actually two surfaces, right? That means we have to calculate the flux on both surfaces. And it says for us to use positive orientation. What do they mean by positive orientation? Normals are going to be going away from it because this encloses a solid, doesn't it? And because it encloses a solid, Positive orientation means vectors moving away. So on this green surface, our normal vector should be pointing which way? To the right, right? So on the green surface, they're pointed to the right, like this. And what about on this kind of orangish reddish surface? To be out to the left, right? So they've got little angles to them because it's on a curved surface. But the y component should be negative for these, and the y component here should be positive, right? Okay, so let's break this up into two surfaces. Let's do this one first. We'll call this one S1. We'll call this one S2. So we're trying to find the flux over S of F dot ds, which for us is going to be the flux over S1 of F dot ds plus the flux over S2 of F dot ds. So we're breaking it up into two surface flux integrals, all right? So what do you think about S1?
S1 is just a standard discipline, correct?
It is. So how would you like to draw S1? We have some options, right? So one way we could draw it is using an R of UV, right? I'm just going to consider this. S1, we could do an R of UV. Do y'all want to go ahead and do it, just to practice it? What would our R of UV be here? How do you draw a disk with a fixed y coordinate of 1? Well, I can do that, right? Okay, so that's the easy part. How do we draw disks again? U cosine V, U sine V, or you could do it the other way, V cosine U. But you said U cosine V, U sine V for our x and z components, sorry. And then here your U and V would be restricted between where and where? So U, 0 to 1, and then that's controlling the radius, and then this is controlling the angle, right? Yeah. So we could do that, right? And then we could do the partials of that and cross them and do all that, right? Yeah. Okay, stand by. Let's see. We're going to kind of go, all right, well, we could do that. Another way is to possibly look at that surface S1. Is it a function of two variables? Yes, that is, we could look at the S1 as y being some function of x and z. What is that function? X squared plus z squared, right? Hold on. No, what the hell am I doing? I know what I'm doing. That's not it. Hold on. That's not it. Can you look at, I was doing the S2, sorry. Can you look at S1 as being a function? What is it? It's a flat plane, right? I mean, it is a flat plane, right? Yeah. So you could look at it as being a function of x and z, right? Yeah. But it's constant. It's always what? Y is always 1. So you could say, yeah, it's a function of x and y, but it's 1 all the time. Yeah. The problem, okay, with this one, we're in business, right? We could do the partials. We got the domain, we're in business. Yeah. This one, we've got a nice function, right? The domain, however, is the projection of that disk over to the xz plane, which is a circle, right? Or a disk on the xz plane, which means we would have to do what? If you're going to try and do a double integral, and you're going to say the domain of this is over here and it's a circle over here, then that shadow on that plane is a polar region, right? So you'd have to convert to polar. So I'm going to go here and I'm going to say, but I would have to go to, I'd have to use polar, right? So that's another option. It's within reason, right? We could do it.